So time for tutorial 5, bias variance trade-off. Bias variance trade-off is one of these universal things we're thinking of when we analyze data. So in this world, I can have strong and simple models. Everything that I see, I'll interpret in terms of those models. I will be quite certain about the parameters of my models, no? Because there's a small number of them and the world will fit them. And basically I can be really sure what the best values for them are. But at the same time, everything will be biased towards my model. Whatever I see, I interpreted it in terms of very simple models. Alternatively, I can have more complex models. Now that produces high uncertainty about the parameters of that. And therefore it produces high variance in the estimates that we have. Now, let's make this concrete. Now, like if we have a first order polynomial here, we have linear data, we can fit something to it. I will be quite, I can fit the linear curve to it. It's just it's just two parameters here. I'll be quite good at doing that. If I have a second order polynomial, my fit will be better. No, but I will probably be less certain because now I have 3 parameters instead of 2. And if I fit a fifth order polynomial to it, my mean squared error gets even better. Look, it starts going through that. And as I keep increasing the order of the polynomial, I'll get better. This is what we see on the right-hand side. Mean squared error on the y-axis, model polynomial order on the x-axis. You can see how we get better and better and better. And if there's like 50 points here, as soon as I give orders of polynomials of order 50, I will get all of them right. Wonderful. Now, which one's the best? I mean, like already, if I asked you, how would you draw a line 30, you would probably give me something that's more like the red line. So, how will we find out about that? The important thing is here we have to consider the bias variance trade-off. The bias, low model complexity means that there will be systematic deviations from the structure of the underlying data. No? So like the equations that I have which have low complexity are bound to be sort of different from the data in lots of ways. And for variance, you can say high model complexity captures variability beyond the structure of the underlying data. So for example here, the fifth order polynomial does a really good fit. It's just not part of the real structure there. Now, you can say if I have data that comes from a second order polynomial and we have data points on that and we do a linear fit, that linear fit will be wrong. Like more specifically, no, you can say if I do it again, it will give us a different value and so forth. If I do it lots of times, I'm gonna get like a relatively narrow distribution of fits to that, which is good. I have low variance in this, but at the same time I'll be biased. Namely, I will undershoot the data almost every time. Here I will undershoot the data. Here I will overshoot the data. Now all the data are like below the lines I'd be drawing in. So in the case of low model complexity, the bias is large. The linear slope always misses many data points, but the variance is small. Our fits, we are very certain about our fits. And the bias is really what you see here. Not here too high, too low, too high. And the variance is small. Now, let's go to a different model. Now we have some data here. We fit a fifth order polynomial to it. What happens there? Now we can get new samples from that. And that gives us now a very different fit. Why? Because, well, there's high variance. No? If we fit all of them, this is the set of different ones that we get of fifth order polynomials. And you can see it's really not beautiful. Every time we randomly sample data, we will get different results. So in the case of high model complexity, the bias is small. The model is really good at basically getting that there is this structure here. But it goes through almost all data points, so it's very close. But the variance is really large, in particular outside of that distribution. And so you can say how should we think about this? Like if we look at the model error, there's an error that we get from underfitting. The linear equation just can't fit this curvature that is real in the data. If we increase the model complexity, the bias will get smaller. But if we increase the model complexity, we will progressively overfit the data. So ultimately, there will be some sweet spot in between where we fit the essence of the data, but we don't introduce a lot of extra variance. The best model is then the one that navigates this trade-off between variance and bias. So model evaluation aims at estimating the generalization error of the selected model, i.e. how well the selected model performs on unseen data. So on the training, what we can do is we can now take the data set and divide it into a training set that we use for fitting and a test set that we don't use for fitting. Now here on the right hand side, you saw the mean squared error on the training set. These are the data that we use for doing that fitting. That's the training set. But now you could say, no, and there you see the bias. In the training set, we will only see we will see only the bias. But now you can say, what if we get more data? Someone just hands us more data. We repeat that experiment. And in that test set then, what we'll find is that if we increase the polynomial order of that, the mean squared error first gets better and then it gets worse again. What's happening? The crazy things here that the fifth order polynomial does don't lead to better fits here for the orange data. It just leads to better fits for the black data that it was fitted on. So the test set error in the end goes up. So the best model for the test set is this one. Now, we spoke about it earlier. What do we want a good model to do? It should be good at predicting data that is yet to come. We don't want the model to primarily describe the data that we already have. So that's why that division between training set and test set is so important. And in the following notebook, you will continue the polynomial regression exercise. You will now take the data and split it into a training set and a test set. And you will fit different polynomial models using the training set and test on the test set. And you'll look at the training error and the test set error, and you'll explore the roles of overfitting and underfitting. Enjoy.